Welcome to the Huberman Lab podcast, where we discuss science and science-based tools for everyday life. I'm Andrew Huberman, and I'm a professor of neurobiology and ophthalmology at Stanford School of Medicine. Today we are discussing placebo effects. We will also be discussing what are called nocebo effects, as well as belief effects. All three of these, placebo, nocebo, and belief effects, are all related to our brain's incredible ability to place an expectation on what is about to happen and actually change what is about to happen, independent of the physical and chemical properties of a drug or some sort of other treatment solution for things like pain, Parkinson's disease, irritable bowel syndrome, asthma, stress, and on and on and on. Now, one of the most incredible things about these effects is that despite the fact that it would appear that they are simply psychological or the power of the mind over matter, it's not that at all. Placebo, nocebo, and belief effects actually change the way your biology, your physiology works. In fact, you have neural circuits within your brain that are dedicated to how your expectation of what will happen actually changes some of the most core biological functions within your brain and body, modifying, for instance, heart rate, blood pressure, the release of specific neuromodulators such as dopamine and adrenaline, and so powerfully so that these types of effects can actually work along with traditional drug treatments or behavioral treatments in order to vastly change the way that your brain and body work. So if you think of the word placebo as an inert substance or treatment that is merely a control, it's merely something introduced to an experiment or a clinical trial to try and figure out, what's happening normally in somebody's brain or body as a comparison to some drug or other type of treatment. Well, while that can be true and placebo controls are vital for certain clinical studies, it's also the case that placebos, nocebos, and belief effects have powerful impact on our physiology entirely separate from all of that, so much so that several highly esteemed researchers in the medical community around the world believe that placebo, nocebo, and belief effects should actually be leveraged in the treatment of various diseases as their own unique treatment. So by the end of today's episode, you are going to have a clear understanding of what placebo, nocebo, and belief effects are, their biological underpinnings, and the way that you can leverage them toward your mental health, physical health, and performance. Before we begin, I'd like to emphasize that this podcast is separate from my teaching and research roles at Stanford. It is, however, part of my desire and effort to bring zero cost to consumer information about science and science-related tools to the general public. In keeping with that theme, I'd like to thank the sponsors of today's podcast. Our first sponsor is 8 Sleep. 8 Sleep makes smart mattress covers with cooling, heating, and sleep tracking capacity. I've spoken many times before on this podcast about the fact that sleep is the foundation of mental health, physical health, and performance. Now, one of the key things for getting a great night's sleep is the temperature of your sleeping environment. For instance, in order to fall and stay deeply asleep, your body temperature needs to drop by about 1 to 3 degrees. And in order to wake up feeling refreshed, your body temperature actually has to increase by about 1 to 3 degrees. With 8 Sleep, it makes it very easy to control the temperature of your sleeping environment. You can dial in specific temperature ranges for the beginning, middle, and end of your night. It even has a sleep tracker, so it will track your slow wave sleep, REM sleep, total sleep, and give you a sleep score. And you can actually divide the mattress into 2 different temperatures if someone else in your bed likes things a different temperature, and they, of course, can have their sleep tracked independently of yours. It's an absolutely wonderful tool. It's completely transformed my sleep, so much so that when I travel to hotels or Airbnbs, I find I don't ever sleep as well as when I have my 8 Sleep. I've even shipped my 8 Sleep out to those places. That gets a little complicated, but that's how much I love my 8 Sleep. It gives me the best possible night's sleep. If you'd like to try 8 Sleep, you can go to 8sleep.com/Huberman to save up to $150 off their Pod 3 cover. 8 Sleep currently ships in the USA, Canada, UK, select countries in the EU, and Australia. Again, that's 8sleep.com/Huberman. Today's episode is also brought to us by AeroPress. AeroPress is similar to a French press for making coffee, but is in fact a much better way to make coffee. I first learned about AeroPress well over 10 years ago, and I've been using one ever since. AeroPress was developed by Alan Adler, who was an engineer at Stanford. And I knew of Alan because he had also built the so-called aerobie frisbee. So he was sort of famous in our community for developing these different feats of engineering that turned into commercial products. Now, I love coffee. I'm somebody that drinks coffee nearly every day, usually about 90 to 120 minutes after I wake up in the morning, although not always. Sometimes if I'm going to exercise, I'll drink coffee first thing in the morning. But I love, love, love coffee. And what I've personally found is that by using the AeroPress, I can make the best possible tasting cup of coffee. I don't know what exactly it is in the AeroPress that allows the same beans to be prepared into a cup of coffee that tastes that much better as compared to any other form of brewing that coffee, even the traditional French press. The AeroPress is extremely easy to use, and it's extremely compact. In fact, I take it with me whenever I travel, and I use it on the road in hotels, even on planes. I'll just ask for some hot water, and I'll brew my coffee or tea right there on the plane. With over 55,000 five-star reviews, AeroPress is the best reviewed coffee press in the world. If you would like to try AeroPress, you can go to aeropress.com/Huberman. That's AeroPress.com/Huberman to get 20% off any AeroPress coffee maker. AeroPress ships in the USA, Canada, and over 60 other countries in the world. Again, that's aeropress.com/Huberman to get 20% off. Today's episode is also brought to us by Levels. Levels is a program that lets you see how different foods and different activities and your sleep patterns impact your health by giving you real-time feedback on your diet using a continuous glucose monitor. Now, blood glucose, sometimes referred to as blood sugar, has an immediate and long-term impact on your energy levels and your overall health. One of the best ways to maintain focus and energy throughout your day, as well as to keep your so-called metabolic health in best order, is to make sure that your blood glucose never spikes too much, nor does it get too low. With Levels, you can monitor how different foods and food combinations impact your blood glucose levels on a moment-to-moment basis. I've been using Levels for some time now, and it's really helped me understand which foods and food combinations, exercise schedules, and sleep schedules are optimal for my blood glucose levels and how that translates to energy levels and other metrics of health. If you're interested in learning more about Levels and trying a continuous glucose monitor, you can go to levels.link/Huberman. Levels has just launched a new CGM sensor that is smaller and has even better tracking than before. Right now, they're also offering 2 free months of membership. Again, that's levels.link, LINK/Huberman to try the new sensor and 2 free months of membership. Okay, let's talk about placebo effects. I will also be talking about nocebo effects. And let's just establish the difference between those. Placebo effects are when an inert substance or behavioral treatment, that is a substance or behavioral treatment that is not going to have any kind of direct biological or psychological activity, right? It shouldn't do anything on its own, somehow does in the direction of improving symptoms or performance. Now let's contrast that with nocebo. Nocebo is when a drug or behavioral intervention, which is inert, it should have no impact on symptoms or performance of any kind, but with nocebo, it turns out these substances or behavioral interventions actually worsen symptoms or performance. Now, oftentimes people will just say a placebo effect. It's a little bit more rare for people to distinguish between placebo and nocebo effects, but I do think it's important to know their difference. Going forward, I'll mostly just refer to these as placebo effects, but I'll talk about nocebo effects a little bit later. I'll also talk about belief effects. So let's just establish what belief effects are. Belief effects are when you or somebody else learns specific knowledge that changes your expectation about what is going to happen in reference to, say, stress or consuming a given food or taking a given drug or doing a specific behavioral protocol. And the specific information you learn or assimilate actually leads to that specific outcome. So in many ways, belief effects and placebo effects are similar. It's just that the word placebo or placebo effects is commonly used to refer to drugs and behavioral interventions. Belief effects are a more specific language used to describe when information of any kind changes the outcome of some physiological or psychological process. Now, what's common to placebo, nocebo, and belief effects is that they all work by changing expectation. And anytime we talk about expectation, we're talking about the function of the nervous system and specifically the brain and specifically the prefrontal cortex within the brain. The prefrontal cortex is neural real estate, which is just fancy nerd speak for the neurons and their connections that reside just behind your forehead, just in the front of your skull. Now, the prefrontal cortex has a lot of different subdivisions or regions. The overall function of the prefrontal cortex can be described as having the ability to either activate or suppress other neural circuits deeper in the brain. Some people, in fact, a previous guest on the Huberman Lab podcast, a neurosurgeon, said the prefrontal cortex can generally be described as the structure in the brain that controls other structures in the brain by saying shh or suppressing their function. So for instance, if you have the impulse to move or to shout, the prefrontal cortex suppresses that movement or suppresses that desire to shout or that shouting. If you've ever had the experience of, going to the edge of a cliff or being on a high bridge and thinking, oh my goodness, you just have this spontaneous thought, which please don't do this in action, but one will have this thought like, oh my goodness, what if I just jumped off? And people think, oh my goodness, do I have some sort of death wish? Well, no. The prefrontal cortex, being largely a context evaluating and prediction machine, is essentially looking at that landscape and predicting what would happen, indeed how bad it would be if you were to jump off that bridge or jump off that cliff. And then you feel that, oh my goodness, what's wrong with me? Why would I think this? But the fact that you think it even for a moment, but you don't do it, and the fact that you recognize that it's sort of a dangerous thought, certainly a dangerous action, again, please don't engage in the action, tells you that your prefrontal cortex is working properly. Again, the prefrontal cortex is involved in suppressing certain types of behaviors. And what sorts of behaviors? Well, the larger theme of the prefrontal cortex that we need to consider today is that it is an expectation or prediction-making machine. It is a bunch of neurons that release chemicals and have electrical activity that are speaking with and receiving information from other areas of the brain, and it's evaluating a number of things like context. What's going on in this room? What's going on in this scene? What's supposed to happen here? What might I do? What should I do? What should I not do? Et cetera, et cetera. Now, the other thing about the prefrontal cortex, given that it has all these different subdivisions, is that some of those subdivisions have a unique, what we call labeled line communication, like a unique highway that leads to specific brain areas that control specific bodily functions, including heart rate, blood pressure, et cetera. And a little bit later in the episode, I'll talk about a specific paper, it's one of my favorite papers, in which a specific prefrontal cortical region is identified as controlling very primitive aspects of our physiology, such as body temperature and heart rate, in reference to beliefs or what's happening in a social scene. And this is very different from the way that, say, getting into cold water or experiencing some other sort of stressor causes increase in heart rate or vasoconstriction. What we're talking about here when we talk about placebo, nocebo, and belief effects are the way in which you learn information or you are told information like, hey, this pill is going to do blank, maybe because the label says it, maybe because the scientist or the doctor tells you that this pill does blank or this injection will do blank. Or maybe you learn some information about what some specific drug or supplement or behavioral protocol will do. And in that learning, you come to expect a specific set of effects. And certain neural circuits in the prefrontal cortex become active and start to activate certain neural circuits deeper in the brain in areas like the hypothalamus. These are ancient, very well conserved across animals, areas of the brain that control very primitive functions. Okay, they exist in essentially all mammals and even in reptiles. The prefrontal cortex also communicates with areas of your brainstem, controlling things like breathing, etc. So the prefrontal cortex is a sophisticated area of your brain that takes into account context, both in the present as well as memories from the past. It can take into consideration goals about the future, and then combines all of that into neural signals to areas of the brain that control basic physiological functions related to the immune system, the stress system, the reward system, the pleasure system, and on and on. So when we talk about placebo, nocebo, and belief effects, what we're really talking about is the ability for information and specific experiences to lead to expectations within us about what's going to happen, and then our physiology of our brain and body fundamentally changes such that those things happen. So let's talk about some specific examples of placebo effects from the research literature. And today we're going to cover a lot of different examples from different systems, but as we do that, I will specifically be selecting examples that illustrate different types of placebo effects and illustrate what those different types of placebo effects are. Now, I should mention that if you're interested in placebo effects, there's a wonderful book that describes many, many different placebo effects and their biological underpinnings in cases where those biological underpinnings are understood. And the book I'm referring to is one that I used prominently in researching this episode. It's called none other than Placebo Effects, Understanding the Other Side of Medical Care. And the book is by Fabrizio Benedetti. I hope I pronounced that right, Fabrizio. And to you Italians out there, if I didn't do it correctly, I apologize. It's an absolutely wonderful book. I confess I've never met Fabrizio Benedetti. I confess I have no relation to the publisher or to the book itself, except that I absolutely love the book. So highly recommend this book. I'll be pulling from a number of different examples described in this book today. To my mind, one of the most interesting examples of placebo effect is where placebo is given and can profoundly change levels of dopamine release in the brain. Now, the study I'm about to describe was done in Parkinson's patients. People with Parkinson's have degeneration of neurons in an area of the brain called the substantia nigra, which is an area of the brain in the kind of bottom back part of the brain. For you aficionados, it's the ventral tegmental area, but you don't need to know that name. These neurons contain dopamine and are essential for the generation of smooth movement patterns, including walking and reaching and moving one's hand to write, etc. And of course, dopamine is involved in a bunch of other things too, including motivation and reward. In people with Parkinson's, depending on how severe and advanced the Parkinson's is, they suffer deficits in the ability to generate smooth movements and often deficits in motivation and reward pathways as well. Now, there are many different treatments for Parkinson's, some more successful than others. Unfortunately, it's still not completely curable, at least not at this time. But most of the drugs that are successful in treating Parkinson's to some degree or another are drugs that increase levels of dopamine within the brain for obvious reasons. As I just mentioned, Parkinson's is a degeneration of the dopaminergic, meaning dopamine containing and releasing neurons in the brain. So people with Parkinson's will often be given L-Dopa, which is a precursor to dopamine, or other types of drugs that increase dopamine within the brain. Now, there have been a number of studies that have compared certain drugs known to increase dopamine, such as L-Dopa, things like apomorphine, bromocriptine, etc., to placebo control drugs. And one of the interesting takeaways from those studies is that, yes, drugs like L-Dopa, bromocriptine, et cetera, increase dopamine and at least can partially or transiently improve symptoms of Parkinson's in many, not all patients with Parkinson's. The placebo drugs given in many of those studies, which were simply a sugar pill or some other inert pill, it doesn't contain any chemicals that are known to directly bind to or increase dopamine in the brain. And yet, nonetheless, when the brains of certain patients were imaged, it was clear that not only was there an improvement in symptomology, but there were increases in dopamine release within those patients' brains, which on the face of it should make no sense. However, when people with Parkinson's or people who even don't have Parkinson's are told a given drug can increase dopamine, and then they put these people into a brain imaging device. It's called a PET device, it has nothing to do with animals. It's the positron emission tomography device. And these people had been injected with or consumed something called raclopride. It sounds really weird and dangerous, but actually raclopride looks a little bit like dopamine itself chemically, and it has a little tag or label on it, and it can bind to certain receptors in the brain where dopamine would normally bind. What was observed is that the placebo itself was causing reduced binding of this raclopride to areas of the brain that have dopamine receptors, which meant unequivocally that there was more dopamine released in the brain, because if more dopamine is released in the brain and parks in those receptors, well, then the raclopride, which looks a lot like dopamine, can't also park or bind to those receptors. Simply put, a placebo drug, again, a drug that has no direct action on the dopaminergic system, if it's given to somebody who has Parkinson's or who doesn't, and they are told, this drug is going to increase levels of dopamine in your brain and potentially improve your symptoms of Parkinson's or have some other effect, well, it succeeded in increasing dopamine levels within the brain, which basically should make us all sit back and say, okay, what are we to think of drugs like L-Dopa and apomorphine, bromocriptine, as compared to placebo? Why isn't everyone just taking placebo? Why aren't we just telling people, hey, this sugar pill is going to increase dopamine? Well, two important points to answer that. First of all, the increases in dopamine that are observed from placebo plus information about what that placebo ought to do for increasing dopamine are not as robust, or I should say generally not as robust, as the increases in dopamine observed from an actual drug known to increase dopamine transmission or release within the brain. The second point is that the structure of the information given to somebody and the belief that they form about what ought to happen, that is the expectation effect, which you'll start to realize more and more across today's episode, that expectation effect really is the underpinning of the placebo effect. Well, the strength of that expectation is really hard to anchor across individuals. And in fact, if people realize they're taking a placebo, the magnitude of the dopamine increase is actually decreased. So this is why we use placebo controls in clinical trials. We want to establish the real difference between the effect of a given drug on a biological system, in this case, increasing dopamine, from the belief or the expectation of what that drug will do. So in that sense, the placebo is really a measure of expectation of what a drug treatment will do, at least in the context of a drug trial. So I mentioned this somewhat complicated example because, first of all, many people are interested in dopamine. We all make dopamine. It's involved in motivation, drive, and focus, and reward, all sorts of things that we hear a lot about these days. Second of all, it really illustrates that placebo, that is expectation about what will happen, is impacting, of course, placebo effects. You realize that now. But it then also has to be the case that placebo effects are playing into any effect that we might observe from taking a given drug or supplement based on our expectation of what that drug or supplement will do. And miraculously, or at least what I find miraculous, is that placebo effects, these expectations based on knowledge and beliefs, are highly specific, which raises all sorts of questions about, for instance, if you were given a drug that increases dopamine levels, but you weren't told that it increases dopamine levels, that perhaps you were lied to and told that it increases the activity of a different neuromodulator like serotonin. Would it? Well, let's explore that because as wild as that seems, it turns out that what we believe about a given drug treatment or behavioral treatment actually has a high degree of specificity. So to illustrate the incredible specificity of placebo effects, I want to describe a study related to hormone function. Hormones come in many different forms. We have testosterone, estrogen, growth hormone, cortisol, etc. There's a study that was carried out in humans in which subjects were informed about growth hormone release and cortisol release. Growth hormone is a hormone released from a gland in the brain called the pituitary. The pituitary has different parts. The anterior pituitary releases growth hormone each night when you go to sleep. It's involved in protein synthesis, tissue repair, bodily growth, appendage growth, and many other things. Cortisol is a hormone that's released from the adrenals. It can also be synthesized and released a couple other places in the brain and body. And it's involved in immune system function, in anti-inflammatory action. A lot of people think cortisol is bad, but it's actually an important hormone for our daily health, our alertness and waking up in the morning, etc. In any event, subjects in this study learned about growth hormone and cortisol and their release, where they're released from, what they do, just as you did. And then their growth hormone and cortisol levels were measured. And not surprisingly, they didn't change. Just learning about growth hormone and cortisol did not change growth hormone or cortisol levels in these human subjects. Now, on days 2 and 3 of this experiment, subjects received an injection of a drug. The drug is called sumatriptan. And sumatriptan is known to increase levels of growth hormone and reduce levels of cortisol. And indeed, that's what they observed. When people received these injections and then their blood was drawn, growth hormone levels went up, cortisol levels went down. Now, the interesting part of the study is a separate day. So after the drug treatments, they come back and they are injected with saline, which has no specific biological effect. It's simply salt water. Okay? They're injected with saline and they experience increases in growth hormone and decreases in cortisol, which on the face of it might seem like, wow, that's incredible. But based on what you've learned thus far in today's episode, you could imagine that knowledge about growth hormone and cortisol somehow combined with the injection to lead to an expectation of increases in growth hormone and decreases in cortisol, which would be amazing in its own right. Okay, after all, saline is inert. It doesn't do anything directly and specifically to the growth hormone or cortisol system. But get this, it turns out that a saline injection, which does nothing on its own, on day 4 or 5, after people have received this drug treatment, increases growth hormone and decreases cortisol independent of what people are told they are being injected with. Even if they're told they're being injected with a drug that has completely different effects than sumatriptan. So Why would this be? How could this be? In fact, there was even a condition in which subjects were told on the day they received the placebo, you're about to get an injection of something that's going to decrease growth hormone. But rather, they experienced a genuine increase in growth hormone and decrease in cortisol in the exact same way they did when they received the active drug, sumatriptan. Okay, so this wild type of scenario has to be explained. And in order to explain it, we need to zoom out from the experiment and ask, what's the similarity between day 2 and 3 of the experiment, meaning the days in which the people received the actual active drug, sumatriptan, that increases growth hormone, reduces cortisol, and the day in which they received the placebo. And the one thing that anchors both those days together, meaning the one thing in common that can explain this effect, is that those were the days in which people received an injection. And in fact, through various control experiments and a few other experiments that were done subsequent to this, because this experiment has been more or less repeated in different forms in different laboratories, it became clear that the brain and body somehow came to expect that receiving an injection leads to increases in growth hormone and cortisol. Now, this is not an indefinite effect, right? People will get injections of other things in the future, presumably active drugs, not just saline, that will change hormone levels or change neurotransmitter levels. But in this experiment, what happened is that there was a pairing within the nervous system. There was somehow a binding of the notion of getting an injection with a syringe, which in the first case was of a drug that increases growth hormone, decreases cortisol. And then when subjects came back and were injected with a different syringe, presumably, I would hope so, with a different syringe filled with saline, even though the saline should do nothing, the body and brain had somehow formed a pairing, an association between syringe, injection, and increased growth hormone, decreased cortisol, which is incredible given that these systems, the anterior pituitary, the adrenal glands, these are ancient systems that, to our knowledge, we can't directly control with our mind. I can't simply close my eyes and grit my teeth and cause the release of growth hormone. I can't simply decide to deploy cortisol from my adrenals, although if I thought about something very, very stressful for a long time, there'd probably be some cortisol secretion. But to our knowledge, there is no way to use thoughts, to use beliefs, to use understanding of knowledge to cause changes in our endocrine glands, right? Our hormone glands, the pituitary, the adrenals. But here we have a case where a drug that increases certain hormones and decreases other hormones, simply by virtue of the fact that it was injected into somebody, leads to a case where subsequent injections, at least in the short run, lead to the exact same hormone changes simply because in the mind and or body of these individuals, injection comes to equal increase in growth hormone, decrease in cortisol, independent of what's being injected. Now, a key point is that had on the final day of the experiment, the subject's been injected with a different drug that, for instance, increases serotonin or reduces epinephrine, I doubt that they would have instead experienced increases in growth hormone and reductions in cortisol. That's simply not the case. The fact that there was only saline in there meant that there was an opportunity for the syringe and the injection, we don't know which, to lead to some sort of paired association in the brain and body that led to increased growth hormone, decreased cortisol, which mimicked the drug effect. But the whole scenario here, as wild as it is, really speaks to the fact that oftentimes we think a given treatment is causing a given effect only because of the action of the drug or the action of a given behavioral protocol. But in fact, the drug and the protocol exist in a big context of different things that the brain and body are integrating and trying to make sense of, and that often gets lumped together. I often say that your brain is, yes, a prediction machine, but it's also trying to simplify things in those predictions. It's not taking into account all the information. It's often lumping information together and coming up with ideas about what's going to happen and why, and doing this subconsciously in a way that, as you just learned, can have profound effects on what happens within us, even at the level of something as basic as hormone release. Now, what I just described is a pretty extreme example, and it's a very experimental condition type example. It's rare that people are undergoing, these kinds of organized receival of information followed by specific drug treatments and placebo injections, et cetera. But you've all experienced the placebo effect in action by way of what's called classical conditioning, simply by virtue of the fact that the smells of certain foods and your past experience of certain foods can lead to the release of a hormone called insulin. Insulin is a hormone that is involved in regulating blood glucose, blood sugar. And typically when insulin levels go up in the bloodstream, glucose levels are going to go down because of the way that insulin controls blood sugar levels. Now, if you've ever had the experience of walking past a bakery or a pizza shop where a delicious smell is wafting out into the environment, you may notice that it, quote unquote, makes you hungry. And indeed, it does make you hungry because presumably you've had the experience of certain smells being associated with the consuming of certain foods, maybe bakery foods, maybe pizza, maybe steak, whatever it is. And the consumption of those foods actually leads to increases in insulin in your bloodstream. Well, there's the so-called conditioning effect, whereby the smell of the food itself starts to lead to increases in insulin. But the conditioning effects of different stimuli, different things in the context of eating and specific foods leading to increases in insulin is actually highly, highly modifiable. So much so that experiments have been done where, for instance, somebody eats a particular food, or in some cases it's just directly injected with insulin, but more often consumes a particular food. And just prior to consuming or during consuming that food, there's a bell ringing or a buzzer in the background going off. And they do that a few times. And then, I'm sure you're anticipating what's coming, somebody can just hear the buzzer or the bell can simply ring and that person will experience an increase in insulin. So what I'm describing is a conditioned insulin response. A stimulus such as a bell or a buzzer that on its own should have zero effect on insulin release has been paired with a food that genuinely increases insulin within the bloodstream. And then even if the food isn't present, the stimulus, the buzzer, the bell, etc., can evoke the insulin response. Now, this is an important example to understand because it's a common one that we've presumably all experienced and that exists within the wiring of our brain right now. But it's different than the smell evoking the insulin response because delicious food, which evokes an insulin response, having a particular odor, that makes sense in the context of food. But here we're talking about something completely unrelated to the food, not the odor, not the taste, not the appearance, just something that happened to be in the environment in which you ate the food, leading to an increase in insulin. And it just screams placebo effect. But it also screams that the placebo effect is strongly modifiable according to context. Again, the prefrontal cortex being the seat of the anticipation or placebo effect, and the prefrontal cortex taking into account lots of things in the environment, trying to understand what's here, what sounds, what smells, what colors, and then lumping all of that together, and eventually, through the activation of specific neural circuits, leading to a very basic hormonal response, in this case, the release of insulin. And of course, what I just described is classical conditioning a la Pavlov. Pavlov won the Nobel Prize for his description of classical conditioning in which dogs could be induced to salivate in anticipation of food by way of a stimulus completely unrelated to food itself. Not the smell, not the look, not the taste, rather just a bell rung before the consumption of food in a dog eventually led to a situation where the mere ringing of a bell could evoke salivation from those dogs. So are we all just like salivating dogs? I guess we are. I'd like to take a brief moment and thank one of our sponsors, and that's AG1. AG1 is a vitamin mineral probiotic drink that also contains adaptogens. I started taking AG1 way back in 2012. The reason I started taking it and the reason I still take it every day is that it ensures that I meet all of my quotas for vitamins and minerals. And it ensures that I get enough prebiotic and probiotic to support gut health. Now, gut health is something that over the last 10 years, we realized is not just important for the health of our gut, but also for our immune system and for the production of neurotransmitters and neuromodulators, things like dopamine and serotonin. In other words, gut health is critical for proper brain functioning. Now, of course, I strive to consume healthy whole foods for the majority of my nutritional intake every single day, but there are a number of things in AG1, including specific micronutrients that are hard to get from whole foods, or at least in sufficient quantities. So AG1 allows me to get the vitamins and minerals that I need, probiotics, prebiotics, the adaptogens, and critical micronutrients. So anytime somebody asks me if they were to take just one supplement, what that supplement should be, I tell them AG1, because AG1 supports so many different systems within the body that are involved in mental health, physical health, and performance. To try AG1, go to drinkag1.com/Huberman, and you'll get a year's supply of vitamin D3 K2 and 5 free travel packs of AG1. Again, that's drinkag1.com/Huberman. Okay, so given that context is a powerful modifier of the placebo effect, and in fact may be central to the placebo effect, I just want to rattle off a few of the known placebo effects that have been demonstrated, which show the extent to which your brain and my brain are coming up with ideas about what given drugs or given behavioral treatments ought to do, and in that way shaping what happens when you take a placebo. Or, and this is an idea that we'll go into in a bit more detail in a few minutes, perhaps context is also changing the way that active drugs, not placebos, but active drugs are impacting your brain and body. The examples I'd like to give are from laboratory studies about the placebo effect, but that relate to very common at-home and normal life scenarios, okay? They are not unique to the laboratory, and they are the following. First of all, placebo effects are strongly modifiable by the expectation of the quality of a given treatment. For instance, if you are given a placebo that has a brand name on it or a name of a drug, it could even be a made-up name. You don't know what the drug does, but it has trademark TM there in the corner of the name, so brand name as opposed to generic placebo. The brand name placebo has a stronger effect. Moreover, if a placebo is placed into a package, not just put in front of you on a little tray or in a little dish, but rather in a package where you have to push it through that little foil wrapping, or you have to take it out of a bottle, and especially if that wrapping or bottle has a label on it, or it looks as if it's a quote-unquote real drug, well then the placebo has an even greater placebo effect. The color of a given drug can even have an effect based on our association or expectation of what different colors relate to in terms of our physiology. For instance, if subjects are given pills that they are told will help them fall and stay asleep, and some subjects are given blue pills, other subjects are given red pills, other subjects are given yellow pills, the subjects that take the blue pills tend to sleep better, even though all the pills, regardless of color, are placebo. They contain no active substance. Okay, so for some reason, most people associate the color blue with sleep, whereas, or I should say by contrast, if people are given a blue, a red, or a yellow pill, and they are told it's a stimulant, the subjects taking the red pill, here I mean the actual literal red pill. I'm not talking about any kind of cultural red pill. I haven't seen The Matrix yet. People tell me I need to see it, but I'm not talking about taking the red pill, quote unquote. I'm talking about taking a pill that is the color red in an experiment. The people that take that pill experience a greater placebo-induced stimulant effect as opposed to when subjects take a blue or a yellow pill. For some reason, the color red is associated with a quote-unquote upper effect or stimulant effect. Moreover, if subjects are given a blue, a red, or a yellow pill, and they are told that the pill will have an antidepressant effect, the subjects that took the yellow placebo get the biggest antidepressant effect. So color of a given pill even impacts the direction, or in this case, the magnitude of the placebo effect. And I should mention that in every one of those studies, yes, there was information about what the given pill should do. It was not the case that if people took the red pill, they felt a stimulant effect. If they took a blue pill, they felt a sleepy effect. And if they took the yellow pill, they felt an antidepressant effect. These were three separate experiments, one on sleep, where subjects were given one of the three colors of pills. Blue had the strongest effect. Or a study of stimulant effects. They were told it's a study of pills that will increase alertness and attention. They were given one of three different colors. The red pills had the biggest effect. And the third experiment, subjects were told this is a pill that will alleviate to some degree your symptoms of depression. The people who took the yellow pill experienced the greatest relief of depressive symptoms. Now that's pretty wild, but what perhaps is even wilder is the more invasive a placebo intervention is, the greater the placebo effect. So capsules have a bigger effect than tablets. I don't know if that's more invasive, but I guess it looks more medicinal to have a capsule versus a tablet. Who knows why, but that's what's been observed. An injection of a placebo has a greater effect than a consumption of a capsule or a tablet, of course. And if people are placed into a medical device or machine, especially in cases where one of their limbs or both of their limbs or even their whole body is placed into a device, even though the device is doing absolutely nothing specifically to our biological system, it is inert, right? A bunch of buttons and a bunch of noises and a bunch of humming as if something were happening, but nothing is happening that directly relates to any one specific biological system except, and now you know what I'm about to say, except expectation of what the machine is doing, well, that has the greatest placebo effect of all. So for some reason, as the level of invasiveness or let's just say the complexity of a given treatment is increased, well, then the magnitude of the placebo effect is also increased. And what this tells us is that the human brain has come to associate level of invasiveness, level of complexity of a given treatment or machine to equate to bigger outcomes. And in some sense, that's completely logical. But again, we have to remember, in absolutely zero of these conditions, whether or not it's a tablet, a capsule, an injection, or a medical device, is there anything being done to these human subjects that impacts a specific biological function except one? And that one, again, is the activation of specific neural circuits in the prefrontal cortex that then are able to communicate with other areas of the brain and body through bona fide biological mechanisms of neurotransmitter release and electrical activity in neurons. This is what the brain does. And of course, the prefrontal cortex being part of the brain, those are the mechanisms it employs to change the activity of hormone-releasing glands, to change the activity of other neurons. In other words, the belief effects, the expectations are real. They are having effects through true biological circuitry. It's just that the pills and the treatments and the machines are not doing anything specific at all except activating expectation. So we've been talking about the placebo effect, and I've been giving examples of strong placebo effects. And while all of what I told you is substantiated by data, I do not want to give you the impression that the placebo effect is limitless, because it is not limitless. For instance, placebos have been used to help in the treatment of cancer, but their effects within the treatment of cancer are limited to a very specific set of symptoms and contexts. So for instance, people who are told a given drug will help them with their cancer by reducing their symptoms of chemotherapy or radiation therapy often experience reductions in the negative symptoms of chemotherapy or radiation therapy, reduced pain, reduced nausea, and by consequence, improved feelings of well-being, compared to people who do not receive the placebo and who are not told, hey, this drug, which in reality is a placebo, is going to help you with your treatment. It's going to make it less uncomfortable. Okay, so in the context of cancer treatment, placebo can reduce the discomfort of various cancer treatments. However, placebos cannot reduce the size or eliminate tumors. If people who unfortunately have tumors, aka cancer, are given a placebo and told this drug, which actually is a placebo, unbeknownst to them, is going to reduce the size of your tumors or eliminate your tumors, that placebo is not effective in reducing the size or eliminating those tumors. This is very important to understand because, as you recall, placebo effects are expectation effects. Expectation effects are driven in large part by the prefrontal cortex and its connectivity to other areas of the brain and thereby to the body. But the outputs of the prefrontal cortex are limited. There are a certain number of them, and indeed there are many of them, but those connections do not extend to tumors themselves or biological systems or circuitries that allow one's beliefs to reduce the size of or eliminate tumors. And this is very important because, unfortunately, there are many sufferers of cancer, and there are many theories about accelerating the treatment of or improving the treatment of or even curing cancer using so-called mind-body techniques or mind-body tools. And we need to be fair to the data which have conclusively shown that reductions in stress, improvements in sleep, social support, a number of things can improve cancer treatment outcomes. Now, those are not placebo effects. Those are all practices for which we know there are reductions in inflammation, reductions in stress hormones that lead to improved outcomes in the context of radiation therapy, in the context of immunotherapy, in the context of any bona fide treatments known to reduce tumor size. So what we need to do is separate out three things here. Behavioral practices such as meditation, sleep, social support, known to reduce inflammation and stress, and that can improve cancer outcomes. Those are not placebo effects. Those are real effects. There are also drugs, radiation, chemotherapy, immunotherapy, and devices known to reduce tumor size and hopefully eliminate cancerous tumors. That would be the hope. Those are real effects. And then there are the placebo effects, the knowledge and belief and expectation about what a given treatment will do. In some cases, it's knowledge about what a given drug will do that improves the outcome achieved with that drug. In some cases, it's people being given a completely inert substance or solution like saline solution, but being told this is going to help with your nausea symptoms, this is going to help with your pain during your immunotherapy, radiation, etc. And those are real effects, but they can only be explained by virtue of expectation and knowledge, aka placebo effects. And I want to emphasize that those placebo effects are not acting directly on tumors to reduce their size or eliminate them. Another example of how placebo effects can be very powerful and yet still have limits to them is yet another study from Dr. Ted Kaptchuk's lab at Harvard Medical School. And by the way, many, not all of the studies that I've been describing today have been done by the Kaptchuk lab. He's done beautiful work on placebo effects for a very long time now. He's considered a real pioneer and a leader in the study of placebo. And he's also been a big proponent of exploring the placebo effect, not simply as a contrast to drug effects or device effects, but as their own specific effect that perhaps can be leveraged in the context of treating disease. So hats off, literally, plural hats off, because they've had so many discoveries in the context of placebo and their powerful effects and their possible uses from the Kaptchuk lab and their colleagues there at Harvard Medical School. Just incredible work. And one of my favorite studies from the Kaptchuk lab is one published in the New England Journal of Medicine some years ago, in which they took people who had asthma. So these are people diagnosed with asthma. These are people who have challenges breathing, and they experience a lot of discomfort in trying to breathe normally unless they are taking their asthma medication. In this study, they took people off of their asthma medication, of course not indefinitely, but for a short period of time. And as expected, those people experienced challenges in breathing and discomfort associated with the challenges in breathing. One group received no treatment. They were just taken off their asthma meds and evaluated, and then of course put back on their asthma meds. Another group received a placebo treatment, and another group received a drug known to improve the symptoms of asthma. Now, what was interesting is that the people who received the drug for the treatment of asthma, not surprisingly, had improvements in breathing and less discomfort. That's exactly what you'd expect. However, the people with placebo also experienced less discomfort in breathing, but their patterns of breathing didn't change. So again, this really speaks to the fact that placebo effects can be very powerful, but that they're very specific. They are not simply wiping out a condition like asthma or completely eliminating all symptomology of a given condition like cancer. This study illustrates very clearly that placebo is effective in reducing the discomfort associated with the challenges of breathing, but not eliminating challenges with breathing per se. Whereas, as I mentioned before, there are drugs, bona fide prescription drug treatments that can both restore normal patterns of breathing and relieve the discomfort. So what this really speaks to is the fact that the prefrontal cortex and its involvement in expectation can have powerful effects on things like pain, powerful effects on things like dopamine, powerful effects on any number of different brain and body systems, but not all of them. Our beliefs and expectations are powerful, as evidenced by the placebo effect itself, but they are not what we call omnipotent. They can't do anything and everything. I'd like to take a quick break and thank our sponsor, InsideTracker. InsideTracker is a personalized nutrition platform that analyzes data from your blood and DNA to help you better understand your body and help you reach your health goals. Now, I've long been a believer in getting regular blood work done for the simple reason that many of the factors that impact your immediate and long-term health can only be analyzed from a quality blood test. Now, a major problem with a lot of blood tests out there, however, is that you get information back about metabolic factors, lipids, and hormones, and so forth, but you don't know what to do with that information. With InsideTracker, they make it very easy because they have a personalized platform that allows you to see the levels of all those things, metabolic factors, lipids, hormones, etc., but it gives you specific directives that you can follow that relate to nutrition, behavioral modification, supplements, etc., that can help you bring those numbers into the ranges that are optimal for you. If you'd like to try InsideTracker, you can go to InsideTracker.com/Huberman to get 20% off any of InsideTracker's plans. Again, that's InsideTracker.com/Huberman. One of my all-time favorite studies in the context of placebo is a paper that was published pretty recently. And the title of this paper is Nicotine-Related Beliefs Induce Dose-Dependent Responses in the Human Brain. And if ever there was a paper that pointed to the fact that our belief systems can really shape the way that different drugs, different supplements, different behavioral protocols can impact the way that our physiology and our brain work, it's this paper. It's a pretty straightforward study. It was, of course, carried out in humans. And what they did is they had people vape nicotine. Nicotine is a known cognitive enhancer. Nicotine, so named because it binds to nicotinic acetylcholine receptors in the brain, which is just fancy nerd speak for the receptors, the little parking spots for acetylcholine, a neuromodulator that's involved in attention, and by virtue of being involved in attention is critical for the performance of certain focused tasks. Okay, so most people associate nicotine with smoking, vaping, dipping, or snuffing. Here we're talking about nicotine that's vaped. However, I want to be very clear, I am not encouraging people to vape nicotine. Yes, vaping is probably healthier for you than smoking, but vaping is not good for you. It would be better to not vape than to vape at all. I did an entire episode about nicotine, so I want to leave aside the issue of whether or not you decide to use nicotine. Okay, that's all covered in the episode on nicotine. I'll provide a link to that in the show note captions. There's a lot of considerations there. It does increase blood pressure and it increases vasoconstriction and on and on. But as I mentioned, nicotine is a cognitive enhancer. It can increase focus and attention, and in doing so, it can allow your brain to do certain things better, like task switching, like focusing in the context of a lot of distraction, et cetera, et cetera. So in this study, nicotine-related beliefs induce dose-dependent responses in the human brain. Subjects used a vape to ingest nicotine, and they were told that they were either ingesting a low, medium, or high concentration of nicotine. And a really nice thing about this study is that they actually measured how much nicotine people vaped. So they were able to measure how much nicotine made it into the bloodstreams of these people. And they were also able to evaluate brain activity in areas of the brain known to have these nicotinic receptors and to also be involved in certain cognitive tasks. So just to get to the grand conclusion of the study, what they found is that people who were told that they ingested a high concentration or a medium concentration of nicotine performed better on a cognitive task that we know is dependent on or can be modified by the amount of acetylcholine transmission in a certain area of the brain than did individuals who were told that they ingested a small concentration of nicotine. Now, the interesting part of the study is that everybody consumed the same amount of nicotine. So here we have a situation where there is a so-called dose-dependent placebo effect. Everyone gets the same amount of nicotine, but people are either told, meaning they were lied to in some cases, that they got a small, medium, or high concentration of nicotine. And for the group that was told that they received a medium concentration of nicotine, they performed better on a cognitive task than did the people who were told they received a smaller concentration of nicotine. Moreover, people who were told that they received a high concentration of nicotine performed better than either the individuals who were told they received a medium or small concentration of nicotine. But as I mentioned before, everyone received the same concentration of nicotine. So this tells us that not only are placebo effects related to expectation, but that the expectation somebody has of the degree of an effect they should experience actually creates a different level of experience. Put differently, if you're told that you're getting a small amount of drug, a medium amount of drug, or a high amount of drug, and that the size of an effect gets bigger as you go from small, medium to high, well, then you will experience the small, medium, or high effect, depending on which group you were in, even if you all got the same dose of drug. Now, I need to be very clear. Everybody got actual nicotine. The placebo effect here is related to what people believed about the dose of nicotine they got, but everyone got active nicotine. Now, here's where it gets really cool. As I mentioned earlier, in this study, they imaged the brains of people that were in either the group that was told they got a small or medium or high concentration of nicotine. And what they found is that in the specific area of the brain that is known to respond to nicotine and that is involved in cognitive functioning related to the task that these subjects were given, they saw increased levels of activity of the neurons in that brain region that scaled up according to whether or not people were told they got a small, medium, or high amount of nicotine. Again, everyone got the same amount of nicotine. They were simply told small, medium, or high, and the brain area itself changed its level of activity, which in turn changed the outcome on the cognitive task, which basically puts everything in a really nice box, wraps it up with wrapping paper beautifully, puts it in a bow, and says, okay, placebo effects are real. And placebo effects scale with the degree of expectation that one has. So anytime we are told that a small dose of something is going to lead to a small effect, a medium dose of something is going to lead to a bigger effect, and a high dose will lead to an even higher effect, well, whether or not that occurs is going to depend a lot on what sorts of quote-unquote effects we are expecting. Again, you can't use placebo to eliminate tumors. There's a limit to what placebo effects can occur. But assuming that the effect that one is interested in is modifiable by knowledge and expectation, well, the size of that effect will scale with how big you expect the effect to be. And it's not purely psychological. That's the point here. It's not just about your beliefs and you doing something very different in the context of a task or in a sports event. Your physiology, in this case, the activity of a specific brain region, increases its level of output according to your expectation of the level of drug you consumed. So in my description of that recently published study, you notice I said placebo effects, but in many ways what I was describing were belief effects. It's a little bit difficult to disentangle what's a placebo effect and what's a belief effect. In general, belief effects have to do with acquiring a bit more information or specificity of information about what the expectation should be. So I suppose the study I just described could easily fall under the category of belief effects and not just placebo effects. But nonetheless, belief effects are powerful. And they're especially powerful because as one starts to layer in different amounts and different types of information as to what a given drug treatment or behavioral treatment will do, one can start to see really nuanced outcomes as well as truly surprising outcomes. And some of my favorite studies on belief effects were done by my colleague at Stanford. She's in the Department of Psychology. Her name is Dr. Aaliyah Crum. She's been a guest on the Huberman Lab podcast before. We will also provide a link to that episode. And Ali's lab studies mindsets. Mindsets, of course, incorporate a lot of things besides beliefs. They involve prior knowledge. They tend to have even more information woven into them than either placebo effects or belief effects. But Ali's really one of the world leaders in understanding these belief effects and has done some just gorgeous work in illustrating the incredible range and extent of belief effects that exist. One of my favorite studies in this context is the paper from Ali's lab entitled Mind Over Milkshakes. Mindsets, not just nutrients, determine the ghrelin response. So here I'll just briefly describe the study. I'll paraphrase the abstract. On two separate occasions, people consumed a 380 calorie milkshake. And they were either told that it was a 620 calorie, quote unquote, indulgent shake or a 140 calorie, quote unquote, sensible shake. Then the hormone ghrelin was measured. Ghrelin is a hormone associated with hunger. It is released from and binds to various sites within the brain and body, but it's generally associated with the hunger response, the desire for food. Then their subjects had their blood drawn at 3 different time points. So at baseline, prior to consumption of the milkshake, anticipatory, meaning just prior to consuming the milkshake, and post-consumption, 90 minutes after consuming the milkshake. And then ghrelin was measured within the blood samples that the people provided. Now, as you recall, everyone is consuming the same 380 calorie shake, but that's unbeknownst to them. One group thinks they're drinking an indulgent shake that has lots of calories. The other group thinks they're ingesting a quote unquote sensible shake with fewer calories. And it's important to note that in the study, the individuals were asked to read the labels of the shake and get information about, okay, this is an indulgent shake, has a lot of calories, a lot of fat, etc. In the other case, this shake has very few calories, it contains healthy ingredients, etc. Now you can probably guess where this is going. The people that consumed the milkshake but were told it was a high-calorie indulgent shake and also, by the way, consumed information about it being high-calorie and indulgent, or they were reading that on the label, experienced steeper reductions in this hunger-associated hormone called ghrelin, as compared to the group that also consumed the same 380 calorie shake, but thought that the shake was a sensible shake with fewer calories, that was a healthier shake. Those people experienced reductions in ghrelin as well, but they were less steep. They occurred less quickly over time. And in addition, their subjective level of satiety, of fullness, or of feeling as if they had enough food to quell off hunger was also related to whether or not they thought they had consumed the higher calorie indulgent shake or the lower calorie sensible shake. There are a bunch of other interesting aspects to this study. I'm just giving you a cursory overview of the major effects, but the takeaway is very straightforward. What we believe about the foods we are consuming strongly impacts the downstream hormonal effects of consuming those foods. Ghrelin, after all, is a peptide hormone that is secreted from the stomach. Okay, yes, the stomach has neurons, but as far as we know, the stomach doesn't have a little thinking brain in there. The stomach is operating in a very kind of crude language of the nervous system as compared to the thinking and analytic language of the brain, the forebrain. But what's happening here is that knowledge, indeed specific knowledge about what more calories means as opposed to fewer calories, what the word indulgent means as opposed to sensible, all of that is being combined and then communicating with neurons and other systems of the gut to literally create a different hormonal response to food. And that's incredible because the hormonal response to food is a very strongly evolutionary conserved set of mechanisms. And yet this study and other studies like it, including the conditioned insulin response that we talked about earlier, Pavlov's dogs, or in this case, we are the Pavlov's dogs. We're the ones that can get conditioned to a bell or the smell of a food or the sight of a sign on a bakery to get an insulin increase. All of that stuff that is primitive, hard wiring of the brain and body is also being strongly impacted by the more, let's call it sophisticated or analytic aspects of the wiring of the brain, such as the prefrontal cortex, such that what we believe is going to happen is actually what happens. Now, the other study on belief effects and mindsets and how they can impact outcomes in terms of our physiology relates to exercise. And this is a study that Dr. Crum herself came about because she was talking to one of her academic advisors. This was before she opened her own laboratory. And, Aaliyah's an athlete. She was actually a Division I athlete. She's an incredibly impressive individual, by the way. She's a tenured professor at Stanford. She was a Division I athlete. She has a degree, or rather a certification in clinical psychology. So she's an extremely accomplished individual, but exercise and athletics have always been a big part of her life. And one day she was talking to her advisor, and her advisor offered the possibility that, and here I'm paraphrasing from a different conversation, perhaps all the positive effects of exercise are placebo. That's actually what her advisor said. And Allie said, no, there's no way, right? And we know that you exercise, you get an increase in heart rate and blood pressure during exercise, but that leads to lower levels of baseline blood pressure and heart rate afterwards, after you adapt to that exercise. And her advisor said, well, okay, that might be true, but why don't you go test it? So she did test it. What she did is she took hotel service workers. So these are people that clean hotel rooms for a living. And these are very active people, right? They're vacuuming, they're changing sheets, they're going upstairs, they're folding laundry, they're doing a bunch of different things throughout the day. And they divided them into two groups. One group was told that doing a great job and being diligent is very good for you. They were told all sorts of things about their job and how it was important. And indeed, their job is important, right? We need people who can perform these roles of turning over hotel rooms and doing those sorts of things so that hotel rooms can be clean and beautiful when we arrive. The other group, however, was told that the normal daily activities that these people were partaking in, the folding of the laundry, going up and down the stairs, pushing of carts, etc., was exercise, and more importantly, that it was the type of movement that could, for instance, lead to reductions in blood pressure, reductions in body weight, improvements in lots of different health metrics. Now, the incredible outcome of this study was that simply on the basis of whether or not people were told and therefore believed that their daily activities would lead to improvements in these different health metrics, reductions in blood pressure, reductions in basal heart rate, reductions in body weight, well, that's exactly what happened. People who received the information about how exercise was healthy and their work mimicked exercise experienced the health metric changes. Whereas people who were simply told, your work is important, it's important to do a good job, et cetera, they did not experience the same health metric improvements. So that provides support for what Dr. Crumb's advisor had suggested, that at least some of the effects of exercise are likely due to mindsets or beliefs, aka belief effects. So throughout today's episode, I've been talking about how our expectations and beliefs and mindsets can impact these really deep layers of our physiology, things like hormone release, things like level of discomfort or pain during a given treatment, and on and on. And I've talked a lot about the prefrontal cortex as critical for understanding what's happening in a given context and for setting those expectations, because the prefrontal cortex, as you recall, is a prediction machine, and context is important for prediction, and on and on. What I haven't yet told you is how it is that the prefrontal cortex actually does this. I mean, what are these magical output pathways of the prefrontal cortex? And while I already established that they are not infinite, right? The prefrontal cortex can't control everything, meaning if I give you some information like, just thinking about and believing that your left quadricep is going to be, much stronger than your right quadricep. And if you just keep perseverating on, meaning you keep thinking about that and looping on it in your mind, and I give you some examples of how, thinking about strength can make muscle stronger and on and on, in the classic context of the placebo effect, all that expectation ought to lead to an improvement in strength and perhaps size of your left quadricep. But that's not what happens. Why? Or more accurately, why not? Well, as far as we know, there isn't a direct neural circuit or hormonal pathway whereby thoughts from the prefrontal cortex can impact the growth of muscles in your left quadricep. However, there are output pathways from the prefrontal cortex to regions of the brain that are known to control very basic bodily and brain functions, such as the hypothalamus. And those pathways are known to be able to change certain parameters of our, for instance, stress response, so blood pressure, heart rate, vasoconstriction, even body temperature. So I just want to take a moment and describe what I consider one of the more beautiful studies illustrating a specific pathway from the prefrontal cortex to the hypothalamus that allows control of the so-called stress response in the context of very specific psychological stressors. Now, this paper is important not just for our discussion of placebo, belief, and mindset effects, but also for any discussion about so-called psychosomatic effects, or the idea that our modes of thinking, whether or not they are related to calmness or to stress, can strongly impact our physical health. And the title of the paper is A Central Master Driver of Psychosocial Stress Responses in the Rat. Goodness, that's a tongue twister. Psychosocial stress responses in the rat. Now, the fact that this study was performed in the rat should not cause us to lean away from it or to think that it's not relevant to humans, because the very same circuitries that are described within this study have analogous circuitries within the human brain. I know that to be true from my work in neuroanatomy, teaching neuroanatomy, and other groups separate from the group that did this study have explored similar circuitries in the human brain. Now, in this study, what they were able to do was to identify these two particular regions, which I'll just call them DP-DTT for short. So instead of saying dorsal peduncular cortex and dorsal tinea tecta, so just say DP-DTT. This is this area of the prefrontal cortex. Okay, don't let these acronyms and names scare you. These are just names of a little subregion within the prefrontal cortex. Send connections, little wires that we call axons, to an area of the brain called the dorsal medial hypothalamus. The dorsal medial hypothalamus is a highly conserved structure, meaning whether or not you look in mouse or in rat or in apes or in humans or in dogs, the dorsal medial hypothalamus contains neurons that are involved in generating cardinal features of the stress response, things like increased blood pressure, things like increased vasoconstriction, things like increased body temperature, things like increased brown fat thermogenesis. Now, we can even go a step further, because that's what they did in this study. They mapped the connections from these specific subregions of the prefrontal cortex, the DP-DTT, down to the dorsal medial hypothalamus and a very specific set of neurons within the dorsal medial hypothalamus. But even there, we're still in the brain. We haven't yet established how activation of these specific neurons in the dorsal medial hypothalamus actually change blood pressure, how they actually cause vasoconstriction in the periphery, because that's what happens when you get very stressed. Whether or not it's from social stress or from cold water, there's a constriction, what we call vasoconstriction, in the periphery, right? Blood is shuttled toward the core of the body to keep your core organs alive. You're still going to get blood to the big limbs of your body so you can move, run if you need to, but your digits, your appendages are going to get far less blood flow to them because of this vasoconstriction. And that's achieved by an output from the dorsomedial hypothalamus, okay, so the second hub along this chain, to an area of the brainstem called the rostral medullary raphe. Okay, again, fancy name. You don't have to remember the name if you don't want to. Maybe you aficionados want to. But what we're doing here is we're moving from the prefrontal cortex to the hypothalamus, then to the brainstem, and then from the brainstem out to what we call the periphery, to the body, to the spinal cord, to the blood vessels themselves, to the organs of the body like the gut and the heart and the lungs, all the things that we associate with the so-called stress response. So as we've been learning about placebo effects and belief effects and mindset effects, and learning that, okay, just our knowledge about something, our anticipation, our thinking can influence levels of a hunger hormone. Isn't that wild? Or can influence the amount of pain that we experience in response to a cancer treatment, or can change the amount of dopamine in the brain in the context of a placebo given to people with Parkinson's. Well, all of that seems very, very surprising until you look at studies of the sort that I've been describing in the last few minutes that are starting to establish the very precise neural circuitries that lead from areas of the brain like the prefrontal cortex that are associated with thought and context and planning and prediction, down to, I don't want to call them the deeper or more primitive layers of the brain, because these areas like the hypothalamus and the medulla, the brainstem, they're not really primitive in the sense that they do very sophisticated things. It's just that they tend to be present in both mammals and reptiles. They're present in fish, whereas the prefrontal cortex is a brain structure that has undergone fairly significant elaboration as you move from animals like, say, cats, dogs, up to great apes and to humans. And at least to our knowledge, as a field of neuroscientists and biologists, humans have the most sophisticated, or rather elaborate, prefrontal cortex, the most number of different subareas of the prefrontal cortex. And every time there's an investigation of those subareas, what they do, what their anatomies are, meaning where they connect to and who connects back to them, it's found that there is a tremendous degree of specificity. All of which is to say that we shouldn't be surprised at all that these placebo belief and mindset effects occur, because there's a clear biological substrate for them. So up until now, we've been talking about the placebo effect as these incredible set of effects that have a real biological substrate. There are anatomical pathways, hormonal pathways, neurotransmitters involved, and that's all true. But what's also true is that the placebo effect can vary in size tremendously between individuals and across different studies. And in fact, this was described in the first formal study of the placebo effect. In that study, it was shown that approximately 30% of the individuals in the study showed a robust placebo effect, but that the other 70% showed a less robust placebo effect. And that result, meaning that variation in susceptibility to the placebo effect, has borne out again and again and again across different studies. Now, modern science has now taught us that if you look at the genomes, the genes that happen to be expressed in one individual versus the next, versus the next, versus the next, there are certain genes, not a lot of them, but there are certain genes that seem to correlate with certain types of placebo effect being greater or lesser in certain individuals. And while there are a lot of these different genes and a lot of different placebo effects, one of the more interesting ones is the COMT gene, which encodes for something called catechol O methyltransferase. Catechol O methyltransferase, as the name suggests, because it has an ACE in there. In the context of a discussion about biology, that almost always means you're talking about an enzyme. Catechol O methyltransferase is an enzyme involved in the regulation of the so-called catecholamines. Catecholamines being dopamine, epinephrine, and norepinephrine. Okay, we've already talked about dopamine in the context of Parkinson's. I've talked about dopamine a lot, frankly, on the Huberman Lab podcast because it's involved in motivation, it's involved in focus, pursuit of reward, it's involved in movement, as we discussed earlier. Norepinephrine and epinephrine also do many different things in the brain and body, but not the least of which is to increase activation state for heightened focus, for increasing the bias toward movement of the body, and on and on. In any event, this gene, COMT, catechol O methyltransferase, seems to show strong variation in individuals that show strong variation in the placebo response to certain types of placebo conditions. And I just mention it because I think it's super interesting. After all, a lot of the studies that have demonstrated placebo effects have shown those effects in the context of changes in dopamine, epinephrine, and norepinephrine. So it's not without context that we're talking about the COMT gene. But also, just as a general theme, the fact that there are genes that encode for specific biological substrates, in this case, regulation of dopamine, epinephrine, and norepinephrine. And those genes show up at different levels in different individuals, and the placebo effects show up at different levels in different individuals. And now there are studies that are starting to show that the levels of those genes and the degree to which one experiences the placebo effect, either elevated response or reduced response to the placebo effect, seem to be fairly strongly correlated. So this again is more evidence that yes, the placebo effect is based on knowledge, belief, expectation, but that it has a real biological substrate. Just as there are anatomical pathways out of the prefrontal cortex to the hypothalamus, down to the brainstem and out to the body, there are also genes expressed in specific cells within our brain and body that allow for our beliefs and expectations that are carried through that prefrontal cortex circuitry to have either a greater or lesser effect. So throughout today's episode, I've been talking about how knowledge, your belief and understanding about what might happen, ought to happen, or very likely will happen, influences whether or not that thing actually happens, the so-called placebo effect or belief effect or mindset effect. And what I hope I've made clear during the course of our discussion is that while placebo effects arrive through our cognitive understanding of what might, ought to, or is likely to happen, the downstream effects, the effects on asthma, irritable bowel syndrome, insulin, growth hormone, pick your favorite biological system. Essentially, every system within the brain and body has been shown to be susceptible to placebo effects. What I hope is becoming clear is that in every case, the placebo effect is a biological effect. It's not just, our thoughts tricking us into thinking something happened that didn't happen. It's our thoughts, our mind, creating real biological effects. If you're learning from and or enjoying this podcast, please subscribe to our YouTube channel. That's a terrific zero-cost way to support us. In addition, please subscribe to the podcast on both Spotify and Apple. And on both Spotify and Apple, you can leave us up to a 5-star review. Please also check out the sponsors mentioned at the beginning and throughout today's episode. That's the best way to support this podcast. If you have questions for me or comments about the podcast, or topics or guests that you'd like me to include on the Huberman Lab podcast, please put those in the comment section on YouTube. I do read all the comments. Not on today's episode, but on many previous episodes of the Huberman Lab podcast, we discuss supplements. While supplements aren't necessary for everybody, many people derive tremendous benefit from them for things like improving sleep, for hormone support, and for focus. To learn more about the supplements discussed on the Huberman Lab podcast, you can go to Live Momentous, spelled O-U-S, livemomentous.com/Huberman. If you're not already following me on social media, I am Huberman Lab on all social media platforms. So that's Instagram, X, Threads, Facebook, and LinkedIn. And on all social media platforms, I present science and science-related tools, some of which overlaps with the content of the Huberman Lab podcast, but much of which is distinct from the content of the Huberman Lab podcast. So again, it's Huberman Lab on all social media platforms. If you haven't already subscribed to our Huberman Lab podcast Neural Network newsletter, the Neural Network newsletter is a zero-cost monthly newsletter that includes podcast summaries and podcast protocols, which are brief 1 to 2-page PDFs that explain in bullet point fashion things like deliberate cold exposure. We have a foundational fitness protocol. We have a toolkit for sleep. We have a toolkit for neuroplasticity and learning, deliberate cold exposure, deliberate heat exposure, and on and on. All of that, as I mentioned, is completely zero cost. You simply go to hubermanlab.com, go to the menu function, scroll down to newsletter, and provide your email. I want to emphasize that we do not share your email with anybody. Thank you for joining me for today's discussion all about placebo and belief effects. And last, but certainly not least, thank you for your interest in science.